This is the empty bucket being weighed at 424 grams. That's just to tear out the water after I put it in. Flow rate on normal shower setting. Flow goes way up when turned to all cold and way down when turned to max heat. This temperature flow combination gives a nice steamy 46.1 degrees C shower at 3.42 liters per minute. This represents a 33.2 degree C delta T temperature change. This is the flow that comes out of my shower, and it's really quite a good one. I mean, it's not bowling you over, but it definitely gets you really wet, and it's a comfortable shower. So that's the flow rate. Now I'm just going to get ready to measure it. Okay, just gonna time this. I think it'll take about 2 minutes to get enough in here, and so I'm gonna start. It's the same flow setting we were using before, which is a pretty good shower. Maybe on the light side, but okay. We're gonna do this and start my stopwatch. We're just gonna let that go for 2 minutes, and then I'll just do the math. Okay, we are now at a minute 55, 56, 57, 58, 59, 2 minutes. Okay. And I'll just give this a quick weigh and then take away the weight of the bucket, and that'll give us our liters per minute. Net water weight in 2 minutes is 7.258 kilograms minus 0.424 kilograms of the empty bucket. Nets us 6.834 kilograms of water in 2 minutes. We divide that by 2, we get 3.421 kilograms of water per minute. Water has a specific density of 1 liter equals 1 kilogram. So the flow rate is equivalent at 3.421 liters per minute. So to calculate the temperature rise, delta T, first we need to measure the water temperature with the heater completely off. In fact, I disconnected the electricity to the heater to make sure the heater wasn't contributing anything. And so my cold water, sort of household water, is 12.9 degrees C. And then when I put the heater on at the temperature setting of the flow, the number 7, which is what I take a shower at, it's nice and steamy, that yields 46.1 degrees C. And if we take away the temperature that was the heat that was already in the water, 12.9, that gives us a delta T, a temperature rise of 33.2 degrees C, which is actually going to be a higher temperature rise than would be required on the boat, because the ambient temperature probably isn't going to be down to 12 or 13 degrees. So now just double checking the electrical. My line voltage in the house is nominally 240 volts. By the time it goes through circuit breakers and wires, we've got a little bit of a voltage loss of about 2 volts. So we'll do the calculations though with 237.9 volts because that's what the heater is seeing. And when the heater is turned on, there's water flowing through the heater right now. It draws 34.2 amps. The simple conversion for power is volts times amps, and at 237.9 volts, drawing 34.2 amps, that's 8,136.2 watts, or 8.1 kilowatts, which is about what the nameplate. I think it calls it an 8.5 kilowatt heater, but it depends on what the power factor is. But so we're going to say it's creating 8.1 kilowatts of power to get that temperature rise that we saw. And this is just plugging in the exact same numbers to validate, to make sure that all the calculations are reliable in the real world. So when I put in the cold water temperature, the comfortable shower output temperature, which yields the same delta T, I tweaked the heat loss inefficiency. I had estimated 5%, but in order to get the 8.1 kilowatts, it's only 2.4% heat loss from the heater element itself to the output of the shower head, which is less than 1 degree. And we can see that because we our desired, what we want out of the shower head is 46.1 degrees C. So we need to get to 46.9 degrees C out of the heater, and that equals, when we do the power equals volts times amps, the calculation yields 8.1 kilowatts, which is exactly what we got when we measured in real life. So it checks out.